So, good evening again, Marco.
Hello, good evening.
Yeah, we had a little cliffhanger session last lecture, so now we're going to pick up on that.
And let's see how far we can go with these technologies, right? Yesterday we said infinite range, and let's see if that really, applies to LoRa and other LP1 technologies.
Yeah, I'll share the screen.
Excellent. So yesterday, just as a very short recap, we're talking about LP1, and we said that they're designed for IoT, specifically for IoT. So while Bluetooth and Wi-Fi and so on were not designed for IoT, LP1 technologies are designed for IoT. So for low power wide area networks, they're long range, low data throughput. This is really important, and high sensitivity in some way, and of course low cost. So we went through these graphs, and we said that the interesting one is this final one, where we have power on one axis and range on the other. And we said that we really want to concentrate on the bottom right side, where we have these technologies that have long range and low power consumption. And in fact, we're going to analyze two of them today, Sigfox and LoRa. So Sigfox, the first one, gains, a range. You can go really long distance because you're using very narrowband signals. In fact, you might remember from yesterday that we said that if the band is really narrow, then you can go long distance. And this is how Sigfox operates. And again, it's designed for very low throughput, few messages per day, low power consumption, low cost. Sensitivity is really high, so 134 dBms minus, of course, and even minus 142 dBms. So one day we will go through this dB math, but just to say that 10 dB difference means 10 times lower signal that you can detect. So this difference is really huge. When we're talking about Wi-Fi signals, usually the noise level is at minus 100 dBms. So now we're going, 42 dBs lower than the noise level, which is kind of mind blowing.
Yeah.
And the way you make sure that the message arrives to the other side is because you send the same message 3 times in 3 different frequencies. It uses unlicensed frequencies, 868 in Europe, 915 megahertz in the US, but you have a limit. In Sigfox, you can send a maximum of 140 uplink messages per day. And this means that you can send also 4 download messages per day, meaning from like the Sigfox network to the device. And
Yeah.
mobility is restricted to 6 kilometers per hour. So you cannot use it in a car, for example, unless you go
Yeah,
really
and
slow.
you said it like uplink. That is when the sensor is sending something to the, in this case, the gateway or the Sigfox
Yes.
receive.
And yes, and the downlink is when the gateway sends a message to the device. And as in IoT, you always send many more data from the sensor to the gateway than from the gateway to the sensor. So how does it work? Do you need to install your gateway? Well, you could install your gateway, but let's say in most cases, it's the cellular providers that install, Sigfox base stations. So you rely on these network operators that offer Sigfox services on a subscription basis. So you have to pay for it. You pay, a couple of euros per month, and then your device can send data. It has a bit of geolocation capability, even without GPS. This is kind of interesting. So as you have many of these gateways, they use triangulation to find out the position of your node. Of course, this is not as precise as a GPS, but at least you know kind of roughly the area where your
Yeah.
device is placed. And you have roaming capability. This is also quite interesting from the business point of view. So if you design your IoT device using Sigfox, well, you can sell it in Italy, but you can also sell it in Sweden with no big difference from the device point of view. So what about coverage? Of course, as it relies on operators, you need to find places where operators, install these base stations. And in blue, there's places which have good coverage, and then this kind of pink is places where they're kind of working on the coverage. And if you zoom into Kalmar, you see that the city and the outskirts are covered, meaning that actually you could use Sigfox there. I
Yeah,
believe
and
many people
I
have.
actually know where that antenna is.
Okay.
It's one of the high-rise buildings, not far from where I live. So
Are you planning to use Sigfox for the course? I
no,
mean,
we actually that's a good question. That we do have a lot of people with the 5Pi, but we have not focused on Sigfox. No, we've
okay.
had students that have used Sigfox. I would say a small part of all students have. Some have used it. So because
Yeah,
I think the PyCom devices get 1 year Sigfox
exactly.
subscription. Yeah.
Exactly. Yes. So there's a way, if you look in the PyCom website, to find out how to activate this 1 year, trial kind of service. Yeah.
Yeah.
And it works fine. The interesting part is that you don't get the data directly, right? So the data is stored in a website, and then you need to find a way to download that data. I believe through MQTT or some other API.
Yeah, it's actually a bit tricky to get
Mm,
like it's not very beginner friendly. Well, I would say
yeah.
the Sigfox. So
No. So the things to remember about Sigfox is that, okay, you get this long distance by going narrowband. That's the way you did it in Sigfox. And second, that you really depend on the operator, right? So you need to find places where the operator installed these Sigfox base stations. So you're not independent, you rely on someone else. Let's move to LoRa. So we, spoke a lot about LoRa. Let's see about a bit more details. So LoRa is a wireless modulation technology, which is based on a proprietary Semtech chirp spread spectrum, technology. And it's the physical layer that allows to have this very long range wireless communication and operates in the free license ISM bands all over the world. And the way they reach long distance is using spread spectrum, which is a known technology that people have been using for long. So in a way, they trade bandwidth for signal to noise ratio. So while Sigfox went narrowband, LoRa goes spread spectrum. It's kind of two different approaches to go long distance.
yeah, but it's
Which
sort of the same frequency for Sigfox and LoRa. It's
yes, absolutely, 868. Yeah. Yeah. So if you look at the frequency band, it's actually 433. Keep in mind that frequency, 868 or 915 megahertz in the US. It is also regulated in terms of power, duty cycle, and bandwidth. So we'll get back to power and bandwidth, but the interesting concept is duty cycle, which may be something novel for you. As these devices operate in the ISM bands, and as you want to save power, and as you want to make sure that this spectrum is used by many different devices, you limit the number of seconds you can transmit data from the device. And in fact, in Europe, we have a 1% duty cycle limitation, meaning that we can only transmit 1% of the time, which looks very limiting, right? At the beginning, you say, that's really, really low. But actually, that's not the case. So in 1 hour, you can transmit 36 seconds. And if you look at the transmission time of these devices, you will see that it's milliseconds. So you can transmit actually quite a lot of data in that 30 seconds in 1 hour. But that's quite important. So you have to do it for a number of reasons. So one is because of regulation. So if, let's say, the postal service finds out that you're using your device more than 1% of the time, well, you're in trouble. Second is if the service that you're using to send this data finds out that you're sending too much data because you're active more than 1% of the time, you're kind of in trouble from the software side.
yeah.
And the third one is that these devices are engineered so that the radios don't overheat because they're transmitting 1% of the time. So if you start sending out, too many packets, your transmitter will overheat and will be damaged. So it's kind of important to keep in mind this 1% limitation.
And
So
also, I think that one thing that could be added, I guess, is that if you like also have a lot of different devices and they are sending all the time, well, there will be a lot of data dropped, I guess,
yes,
because
you will get data drops. Actually, getting these collisions is not that easy because again they're transmitting very short, time, and as there are so many different parameters that you can set, it's really hard to get two devices sending data exactly at the same time. And if they're not sending exactly at the same time, then you don't have any issue with collisions. But yes, absolutely. So as we're talking about hundreds or thousands of devices, that might well happen. So this the special thing about LoRa is the modulation. And the modulation happens in what is called chirps, which is also the same technology that we use in radar signals. And so you have what they call up chirp, which means that the frequency increases over time. And then you have down chirps, which means that the frequency decreases over time. So there's some people that sing at that time to make it more clear, but I will not go through that exercise. But up chirp. Okay, there you go.
Yeah.
There you go. And what about the down chirp?
Yeah.
Excellent. Excellent.
Okay, I'm trying my best.
Yeah. And so the physical layer has what is called a preamble. So you send at least 10 up chirps. You see that this frequency going up, and then 2.5 down chirps. That means that you're sending a packet, and then you have data where information is transmitted by changing this frequency. So you see there, sometimes you're going up, and then you're going, up for some time, and then down for some time. So that's the physical layer. And what you should remember is that you can really get very, very high sensitivity with this kind of physical layer. There's many, many different parameters that you can change in LoRa. In fact, they say you have 6,000 different settings. So one is the bandwidth. So bandwidth is the width of the spectrum occupied by the chirp. So you have 125 kilohertz or 500 kilohertz if you're using more bandwidth. The spreading factor, which is the number of bits encoded per symbol. This is kind of interesting from the practical point of view, because if you have a higher spreading factor, if you have 12, this increases the communication range because the sensitivity is higher. So it will take longer time to transmit a packet. So you will use more energy, but you will be more sensitive, which means that you will be able to go longer distance. Then you have the coding rate, the transmit power that you can modify, and the carrier frequency. So again, all of these you can change in many different ways. So at the end of the day, you get more than 6,000 different settings. But I would say interesting ones are the bandwidth. So you have to make sure that you're using one of these allowed bandwidth, and the spreading factor is what you usually change in the device. As we're talking about LoRa, you have one device transmitting and one device receiving. So you have to make sure that they use the same parameters so that they're able to communicate. We said that they have different frequency bands. In fact, that's kind of interesting. We live in what is called region 1 of the ITU, which means that we use 868 megahertz, and the maximum output power is 14 dBm. In the US, they use 900 megahertz, a bit more power. But then if you go to Asia, it's a bit more complicated. So you see that have different frequencies, different powers. But the point here is that when you buy these LoRa devices, you have to make sure that you're using, the appropriate frequency. So if you buy something in the US, it will use a different frequency band. Just to give you a few examples of how powerful is this LoRa, and to answer, our question, how far can you go? Just a few examples. So this happened last year. So they used a big dish radio telescope in the Netherlands, and they pointed to the moon, and then they were able to pick the signal back from the moon. So that means 700,000 kilometers, which is kind of, again, mind blowing, right?
Yeah.
And that was sent through LoRa with, our devices, kind of, low-P devices. So it's really quite incredible. This uses a 400 megahertz band, which is a ham radio band. It was amplified 350 watts, and it used a 25-meter dish. So, it's an experiment, but still, it shows that the transmission is really, really, able to detect the signal bouncing on the moon. Other example, a bit easier, something that you can do in your home, is something called tiny ground station. And so the idea here is that you have some satellites that are moving all the time, of course, and that are sending LoRa signals to the Earth. And you're able to detect and decode these signals from ground stations, so from devices that you install on the roof. And in fact, there's 3,000 members all over the place. There's many in Sweden as well, and they're picking up these LoRa signals coming from satellites. So you have a bunch of satellites, dozens of satellites, which mostly nowadays use the 400 megahertz band, and they send short messages on the Earth. But again, you're able to detect them and decode them with really low cost devices. So this is what you find on the TinyGS website, and it says you have this Norby satellite, for example, which is sending data on 400 megahertz through LoRa. It was received by one station, but there is Phospha something, which again is using LoRa at 400 megahertz, received by 57 stations. So you get some information about the satellite, the power the satellite is using, the temperature up there, gyroscope, how it's moving. But this is an example of something I picked up from my institution. And you can pick up a satellite which is 1,000 kilometers far away, and that's actually not the longest one. You can pick up satellites which are 2,000 kilometers away. Actually, the satellite is not that far. It's always about 500 kilometers above the Earth, but then you pick it up when it's really low on the horizon. So this link is super long. But again, it's kind of mind blowing, right? You're picking up a signal with a super low cost device. This is like a 25 euro ground station that you can buy. It's the ESP32 based device, and you put it on the roof with a small antenna, and you're able to pick up signal from satellite, which is 2,000 kilometers far away, just because LoRa is such a good protocol.
Yeah.
Which again is quite incredible. Okay, but that is LoRa. So again, LoRa is the physical layer. So let's say that you have LoRa device, a LoRa module on the left, node 1, which is sending a packet. So you have the radio part, the kind of the red part. You have a microcontroller, maybe you have some sensors and a power management. So this packet is broadcasted in the air, and that is what is in the header. It says from device number 1 to device number 2. And this packet will be received by node number 2, but also by node number 3. So it's sent on the air, and these other devices receive the packet. Node number 2 will, decode the data, and we're in business. So there's a transmitter and a receiver. That is how LoRa works. So this is kind of basic, right? So you need to have a way, for example, to encode packets to ensure that you have, secure transmission. And to do that, people developed LoRa 1, which is based on LoRa as the physical layer, but it adds many more features, as we will learn in a second. So this is a communication protocol. Yeah,
and when we say LoRa, often like we say it with something that's using LoRa, we often, I guess, mean LoRa 1.
Yes.
But LoRa, as you mentioned earlier, that's the physical layer. And it actually, if you have two devices and they have a LoRa transceiver, well, you can send data directly between these devices using LoRa. Then, well, There is no encryption. If you want to implement it, you have to do it yourself, but it's the physical layer. But when we usually speak about LoRa, I guess, like, it's sort of often mean LoRa 1.
Yeah, even in many papers, right? People kind of,
Yeah.
I wouldn't say confused, but they say LoRa and they mean LoRa 1. But actually,
Yeah.
LoRa 1 is a bit more complicated, and yeah, it's much more complete, right? And it has to do with the architecture. So you want to use this LoRa physical layer because, as I said, it's so powerful. But then we want to add some more, intelligence in that. And in fact, LoRa 1 is open source, freely available, and it's specified by this LoRa Alliance. What is interesting is that it uses a star of stars topology, which means that the devices are like the endpoints of a star, and they all send data to a device which is called a gateway. So you have now two actors. While in LoRa, all the devices are the same. You have these nodes that send data, from one node to the other. In the case of LoRa 1, you have a node sending data to a gateway. They have something called adaptive data rate to improve performance. This is kind of interesting because we said that in LoRa, you have to make sure that one device, the transmitting device and the receiving device, have the same parameters. That's not the case in LoRa 1 because the device automatically adapts these data rates and it finds the best way to send data so that, again, you don't have collisions, you don't waste any energy. So it's kind of much more complicated and much more complex. You have multiple levels of security. Yeah.
I got a question here before we move on to further,
Sure.
like too long, because TinyGS, is that anything that are you able to just get up and running there? Like, who owns that, or is it enthusiasts or researchers yeah?
It is, yeah, it's a very good question. It's like a community based, I would say. So no one owns it. It is not that useful, meaning that you just pick up these broadcast messages from the satellite. So people do it mostly for fun, I would say. If you're a ham radio licensed person, then you can also send packets back to the satellite, which makes it more interesting, right? So now you can have a weather station and you can send data for free back to the satellite. But that's kind of a bit more complex. It's a super active community though. So yeah, and all the satellites
you would recommend people that, like, if you're interested in TinyGS, you should definitely look it up, I guess.
Yes, absolutely. They have a Telegram channel, which is super active. I would say they have, 100 messages per day. Very, very active. So people experiment with different sort of antennas. They have rotors, so they tend to kind of point the antenna to the satellite, so you can kind of follow the satellite while it's moving, so you get more packets, and it's kind of interesting, yeah. So LoRa 1, we said that it also has security, so it has some built-in security, and we'll get back to that just in a second. And so we said that you have different devices. So the, of course, most interesting one is the end device or the mode or your, IoT node, which can only communicate with gateways. So two nodes cannot communicate directly. You need to go through a gateway, and then through the gateway, you get a connection to the internet. It has a 16-bit identifier, which is called DEV-EUI, which is unique to every single devices. And then, as you will see, it gets another address from the network when it joins the network. But the point here is, again, these nodes can only communicate with a gateway. That is special about LoRa 1. You have different classes of devices. Maybe that's not super important, but it's just to say that class A devices are the one that send a message and then they go to sleep. So the window where they can be reached by the gateway, as we said, it is called a downlink, is really, really small. Okay, so you want to just be able to send data. And at the other side, you have class C devices, which are devices that have a much longer receiving window. Okay, so if you want to communicate with a node, let's say you want to, for example, activate an actuator, a small motor of some sort, or a light or something, you want to have a class C device or a class B or a class C device. In a class A device, you need to wait for the device to send some data, and then there's a small window where you can send data back.
Yeah.
Okay, so
and the
I would
thing
say
is that if you have these devices, we had just this battery lecture, and we have these devices that are running for 10 years, then they are like most likely a class A device if it's LoRaWAN. They wake up, they send some data, they go to sleep, and then you cannot communicate with them. So and if it sleeps for an hour, then you have to wait an hour before you can actually send something to the device. So
yeah. So this is architecture. So at the beginning, it's a bit confusing maybe, but I hope you will get clear idea in a second. So on the left, you have the end devices, which are our LOPs or our nodes, which send data. So this data, or they broadcast data, sorry. This data is received by one or more gateways. So this device on the top here is broadcasting data. This data is received by one gateway. This device here, the second one, is broadcasting data, which is received by two gateways. Same for three, only received by one. The fourth one is received by two gateways. So these gateways are very dumb devices. You might think that a gateway is sexy device, but actually it's not. It's usually called a packet forwarder. So these gateways forward packets from the end devices to the internet in some way. In fact, you see here on the left, you have these devices which are on the field, and here on the right, you have other devices, a system which is on the internet. So these devices have to be connected to the internet. These gateways have to be connected to the internet in some way. So either through Ethernet, for 4G, Wi-Fi, whatever. So a packet is sent by the end device, received by the gateway. The gateway simply passes this packet to what is called a network server. So this is a device, a server, that receives packets from the gateways, checks if you have the same packet received by more than one gateway. In that case, it discards the duplicate, and it finds a way to send that packet to the appropriate application server. So if you think about your IoT nodes, they want to send data that have to do with a specific application. So let's say you have a weather station that will send temperature, pressure, and humidity. Let's say that you have a tracking device that will send GPS information. So those are different applications. So this application server makes sure that the data is decrypted. We'll get back to that in a second, and sent to the appropriate application server, which then is linked to some application in some way. Okay, then again, might look confusing, but the important points are that end devices can only communicate with gateways. Gateways are dumb devices that forward packets to the network server, which simply checks if you have duplicates, and then it sends the data to the appropriate application server.
Yeah, and I think it's important to point out from this picture, because this is a common misunderstanding when you start working with IoT, and you connect your device to Wi-Fi, and your device gets an IP address, and you can directly with your device connect to the MQTT server. But now you have all these layers in between. So your device never gets an IP address. You can't really directly communicate with the device. You're dependent on the gateway, and also that, the gateway successfully also transmits any payload to the end device. So just to clarify those things, because I know that these are often the questions when you start with LoRaWAN, is that you really have to think that it's actually the application server that's where things are like on the internet. Or...
Yeah, exactly. Yeah, so yeah, again, you have to think that the end devices work for one application. I think if you start, thinking about that application, then maybe things are a bit clear. So as you say, you have these different layers, but the main goal is at the end your end device sending data to a specific application.
Yeah.
And
I got the question also, Marco.
yeah,
Maybe you have that later on in the slide, but the payload size of LoRaWAN.
I will. I think it's in
Okay,
one
then
of the
we'll.
later slides. Yeah.
Yeah.
Yeah. So the point is that we said that all this information is encrypted, right? So in the next slide, we'll show how that encryption works. So let's say that you have an application, a water meter, the yellow application on the left, that wants to send this data of 123 over this LoRaWAN network. And you have different applications there. You see you have a pet tracking application, a smoke alarm, trash container, many different applications. But we want to measure water consumption. So we broadcast that message. That message is encrypted by the water meter LoRa device. Okay, so instead of sending 123, it sends an encrypted message. So this encrypted message will be received by two gateways that will only receive the encrypted message. So they will not know that that value is 123. And there is no way that on the gateway you can decode that message. You will see a packet, but that packet is encrypted. So you cannot do anything with it. The gateways are connected through Ethernet or through 3G or 4G or whatever to a network server. So they send these two packets, which again are encrypted, to the network server. The network server decodes part of the packet, and it finds out that the two packages are exactly the same. So one of them can be discarded. We don't care about having two packets which are exactly the same. It's the same information. Okay, so you need to decode part of that packet in the network server. That part that you decoded tells the network server which application is interested in that packet. And so the network server sends the packet to the appropriate application server, which has the key to decode that packet. So I think interesting point in this is that when the data travels through the gateways, is encrypted. So if you own a gateway, if you place a gateway on your roof and you pick up one of Frederick's packets, you will not be able to decode it. That's quite important. And the second one is that you need two keys in the system. So one key in the network server to be able to decode at least part of the packet to find out where this packet is going to be sent. And the second key to be able to decode the packet on the application server. So in fact, in LoRa setup, when you're going to get your hands dirty with LoRaWAN, you will always find these two different keys. And you should remember that they are used in the network server and in the application server. There's two ways you can exchange keys. So we said that we have keys, and it's kind of interesting how you authenticate with these keys. So this is, again, the same idea. You see, you have these arrows on the bottom here, say metadata encrypted by the network session key. So this is the one interesting for the network server. And then payload is encrypted by the application session key. So these have to do with the application. You see that the device broadcasts the LoRaWAN packet. And this, again, just a reminder, is done on 868 megahertz. It is received by one or more gateways, which then send the data to the network server, which discards duplicates, decodes the header to determine the application and forwards it to the application server. So then the application server decodes the payload and performs any specific action. So if you look at it here from the transmission point of view, this is again LoRa frequency, so 868 in Europe. This happens on a backhaul to the internet, so cellular, wired, satellite, whatever. And these servers may be co-located, or they could be in different parts of the world. So the network server might be in Sweden, the application server might be in the US. They're usually co-located, but they might be in different places. Okay.
Yeah, I got a question here about the issues of packet loss. Yeah.
That has to do with this layer, right? The physical layer.
Yeah.
So you might have packet loss, and in fact, when you decode many packets in LoRaWAN, you will see that you do have a bit of a packet loss. That is, part of this. They call it lossy environment or lossy, transmission channel, and you do have some packet loss. But then again, you're sending information just from the node back to the gateway, right? So you do have some packet loss, yes. And how do you get these keys? So there's like two ways to do it. So one is for the node, for the end node, to ask for the keys to the network and application servers. So the device asks to be authenticated, and then it is allowed to send data on the network. The other way, which is the, I think, quickest and maybe easiest way, what we normally do in our labs, is that as you set up this application on some sort of server, you can get these keys. So you can get this application key, the network key, and the device address, and then you program your end node with these three pieces of information. Okay, so you go on a server, we'll get back to the server just in a second. You get these three keys, you copy them, and then when you program your device, you have some fields where you need to fill in this information: the device address, the application key, and the network key. And then that device is ready to send data on the network. This is called ABP, activation by personalization.
Yeah. And this is, I might add that a lot of that, it's not the recommended. So if you read up on the documentation on the Things network, and also I think if you're using Helium, I don't even think it is possible by using this. Because then if you get hold of the end node, you can actually extract those keys, and you'll be able to sort of copy that and listen into the data if you get hold of the end node. So
this is one issue. The other issue is that there's no way to know from the node point of view if you're in the range of a gateway, because now you do have the keys on your end node, you're broadcasting packets, and you have no idea if these packets are received or not. So the other way in which you're asking to the network if you can send data, you receive a message back from the gateway. And so at least once you know that you're in the range of the gateway. So it's much more secure. On the other hand, you're kind of wasting a bit of the spectrum, because you're sending one message, at least from the gateway, to the end node. And so that is a waste in some way. So this ABP is less secure. There's no guarantee that you're in range, but you're kind of optimizing the use of the spectrum. Again, I know this is a bit confusing at the beginning, but I hope it is clear. So now if you look at this picture, you see that part of this is hardware. So the end nodes, those are devices. The gateways, this is a dumb device, but it's a device. And then you have these servers, so network server and the application server. So those are, again, servers that offer these two services. So there's organizations and companies that offer these two services. So the application and the network server. And one is called TTN, which you might have heard about, which stands for the Things Network. So they have what is called a manifesto, and they said that they controlling the network makes it possible to control the world. We believe that this power should not be restricted to a few people, companies or nations, but instead this should be distributed over as many people as possible without the possibility to be taken away by anyone. So the Things Network started with this idea. So the idea is that Frederick installs a gateway in his home, and you as a final user should be able to use his gateway to send data on the internet through TTN. And when you install a gateway in your home, Frederick should be able to use your gateway. So it is kind of a good idea. Think about Wi-Fi. You're now at university, but you're not using the Wi-Fi at home. So why shouldn't someone else use your Wi-Fi at home? So it's about this, sharing infrastructure. Yeah. It's completely open source. So the backend is open source. You find the code on the web. So this makes sure that no one will ever, limit you in using TTN. They have, quite a number of people. It's used in 151 countries, so all over the place. And they have about 20,000 gateways. So don't forget this number, 20,000. So that's a lot of gateways. And again, those are gateways that you can use. And TTN provides the application and the network server for free up to a certain level.
Yeah, and also we can see the TTN mapper, you're into that, but I think a lot of universities have TTN gateway. We have one in our campus, and I think you're able to find them often in research lab, universities, and also a lot of people that are interested in IoT might put up a TTN gateway. They are also very cheap. You can buy these for, I think the cheapest option is their own TTN indoor gateway, 70 euros or something like that.
Even less than that. Yeah. It's quite cheap. Yes. And again, this idea of sharing infrastructure, I think is kind of interesting. There is a website called TTN Mapper where you can see the gateways installed in different places and in some way a rough estimation of the coverage. And so this is an example of Switzerland, where there's many gateways. You see 21 in many more than 21, hundreds in around Zurich. So the idea is that all over the place in Switzerland nowadays, you can get coverage from TTN. They installed it on postal offices, in, again, universities, schools, and so on. So the idea, again, is that the final user shouldn't be limited by installing a gateway, should be able to use an existing gateway. This is a Calmer, so I think there's 4 of them, right, in the area.
Yeah.
I couldn't get the
one of those is ours, and the middle one.
Okay.
Yeah.
I couldn't get from the TTN mapper the coverage anymore. I don't know if they changed that. So there's one kind of issue in TTN is that they moved from a version 2 to a version 3, and that was supposed to be super easy, but actually many people didn't upgrade their devices, so they live in this limbo of which version they're using. So that caused a bit of a headache. Second solution, if you don't want to use TTN and you want to own the whole thing, so you want to have your own application server, your own network server, you can install ChirpStack. ChirpStack is completely open. They have this MIT license. You can download it for free. You can install it on a Linux machine. You can install it on a Raspberry Pi, and you will have your own infrastructure, which has advantages and disadvantages, of course. So advantage is that you are in charge, so there is no limit. You can install as many devices as you wish. You own the whole thing. Of course, disadvantage is that you can only use gateway connected to ChirpStack. So in the case of TTN, you have 4 in Calmer and only 1 is owned by university. The other 3 you can use for free without questioning who is the owner of that gateways. If you're using ChirpStack, you're kind of limiting yourself to your own gateways. The third one is helium. I have just 2 slides about helium. Then I will ask Frederick to comment on that. This started how long? Maybe 2 years ago, something like that.
I think the company might have started much earlier than that, like 2013, something like that.
Oh, okay.
But they haven't worked with LoRaWAN for maybe it's 3 years or so. But
Okay.
quite recently they're into the LoRaWAN space.
So it's kind of the same. It's people-powered networks, as they say. So you install a gateway, and users can use your gateway, but there's a business model behind that. So the issue with TTN is that you do it by your, I don't know, generosity in a way, or you volunteer to install a gateway, but there is no mechanism so that you get rewarded to do that. And so it is actually difficult to scale up, right? Why should someone buy a gateway, install a gateway in his home? So in the case of Helium, you do get paid for the traffic that go through your gateway. And I think that has been extremely successful. They have 800,000 gateways installed, or hotspots as they call them. So again, don't forget, TTN 20,000, Helium 800,000. So it's 50 times bigger. It's huge. It's really massive. And again, looking at Calmer, I think that those are, I don't think those are gateways, but those are points that have been kind of tested, right?
No, they are actually. What we're looking at is that each hex in this map is a gateway, and it actually can be more than one gateway. So a hex in this, it's an area of, I don't remember now, but let's say 200 meters or something like that, a hexagon. So there should be a gateway. At least the system thinks that there is a gateway. So.
And
yeah, we have a lot of them.
Okay.
Yeah, but you can see that same thing in a lot of the I would say Western world cities. So in the US, it started firstly in the US, and then in Europe now. You see them all over the place. I guess that in Trieste you have also a lot of helium gateways nowadays. So.
And how does this business work? I mean, are people rewarded by the traffic or by the potential traffic?
Yeah, it's actually a mix. It's the thing with helium is that they what they did, and I can just mention that we have a quite interesting guest lecture from last year when we had helium on board talking about exactly this. But it's cryptocurrency, so they don't pay money. So you're not receiving any fiat money. You're getting these cryptos instead. And obviously, they're not worth anything until you actually get someone that wants to buy them for money.
Sure.
But the thing is that there are exchanges, and you can actually exchange those for fiat. So in the early era, which is when we're talking in early in these terms of technology and IoT, 1 year, that's still a long time ago. You could actually have a quite good payback time for deploying a helium gateway. So the gateway is a bit more costly than the Things network, but you could have a payback in everything from a month to a year, and then you actually earn your gateway back. You will actually get rewards for that, and the rewards are based on mainly proof of coverage and also packet transfers. So if there is a lot of sensors that is sending data to your gateway, then you will get the reward for that. So that is,
many,
I mean, yeah.
Are there many people using the gateways? I mean, final users?
We have seen, we have actually seen quite a good raise in traffic, but I would say that this is still like the hen and the egg problem, like what comes first. In this case, the network comes first, and then we'll probably see more applications when there is a network. But we see all the time that there are popping up things. And as you said, everything is encrypted, so you have absolutely no idea what is transmitted. But I think at this moment, this is one of the, I would say, the networks to choose from, just by looking at the coverage. Yeah, and in numbers, it will work all over the world. It's the same console, everything, and yeah, you have 800,000 plus gateways compared to the TTN 20,000. But still, what we are using at the university is the Things network. Like we deploy the Things network server, and that is actually mainly what we use for students and indoors. So it's not easy to say that something is like better or worse than the other. But if I were to deploy something that would have worked both in Trieste and in Kalmar and also in Stockholm and Berlin, and I want that to be working as good as possible in all these places, I would definitely go for Helium as it is now.
Sure. Yeah. I mean, it's 50 times bigger in terms of gateways. And if the concept is that you want to have, many gateways so that you don't have to think about gateways, I think, it's kind of clear.
Yeah, but there is a cost to this. I mean, the Things network you can use for free, as you mentioned.
Yeah.
They're like zero cost. Obviously, you can rely on someone else's gateway, but if you buy your own, they are also very cheap. So as we said before, you can build your own gateway. I think the Pi-Gate might be one of the cheapest options. I'm not sure, but like the TTN indoor gateway, but 50 to 100 euros, you'll get hold of a LoRa gateway. But in terms of Helium, I think you need to 5 times that price. So they are more expensive. So also you need to pay for the data. So if you're using the Helium network, you need to pay. So, but that is how much do you need to pay? It's not much. So to make an example is that if you have a sensor that is sending, let's say, a package every 20 minutes, for a full year, it will be less than, I think, 50 cents, euro cents, or something like that. So it's more or less like nothing.
Nothing. Yeah, exactly. Yeah. But still, you have to, I imagine, create an account, right? In some way. So my point is, it is a barrier maybe for, practitioners and kind of researchers. While in TTN, you don't have that, right? It's a bit easier.
Yeah, there are differences, and it's good to know that there are. But I would say that almost everything within Helium is also open source. So you are actually able to deploy the backend for yourself and utilize the network. So, but yeah, you're still dependent on the value chain of dealing with crypto and all those things. Yeah, and that many might not be into that area, and they are a bit afraid of that. So then you might not use it. So
okay, so if we want to like categorize, we could say TTN maybe easier to use, completely free, good for research, and then you have Chirpstack, which is the fully open and fully in control version for maybe people that want to host things in their own servers. And then Helium, a bit more adventurous because, again, as you say, it's crypto and stuff, but wide coverage all over the place.
Yeah, really. And obviously, you might have more slides, but there are all these city networks. So at least in Sweden, we see that a lot of the municipalities, they are putting up their own LoRaWAN gateways. And they are not running TTN, they are not running Chirpstack, they are mostly running, I think, with maybe Actility, like the French provider. And they're not open. They're not open. So you need to ask for someone to get subscription. And then, so there are all these options. But essentially, as you already said, that all these LoRaWAN networks, they work essentially the same way. Like end nodes, gateway, the same physical layer, everything. It's more or less like how is the business model and what is connected to what. So
exactly. Okay, something worth mentioning, I think, which is a huge advantage, again, that wasn't there a couple of years ago, is that as LoRaWAN is like a protocol you're using the physical layer of LoRa, you have many LoRaWAN certified products, which is, again, a huge advantage, which means that if you have, a client or a colleague or, you yourself, you want to work on a specific application, you don't need to, buy your end device, solder some sensors, add the battery. You can go in one of the many websites that offer LoRaWAN like marketplace, and you can buy a ready to be used device. Okay, so if you're into, I don't know, fridge monitoring, you can look for that specific device. You simply need to add in the device these keys, these three kind of magic keys, and then you're ready to go, and you send data either to Helium, to TTN, to ChipStack, or to your private provider. So that is kind of unique, and I think it's a huge advantage of LoRaWAN. Are there any questions, Frederick?
Yeah, and I'm sort of answering some questions
Sure.
while we're speaking. So what's the coverage of a gateway? And
Oh,
I
that's
actually answer that it depends. So
unfortunately, it depends. Yeah, exactly.
yeah,
Yeah.
so obviously I would say that if you buy these indoor gateways, like the cheap indoor gateway, the TTN, that's really it's a nice gateway. You put it like just into your power outlet, and it has an internal antenna. I am actually surprised by the coverage of that one,
Mhm.
because we installed one of those at a farmer's place south of Kalmar, and it was several hundreds of meters out on the farm, and we still receive data. So even those can go hundreds of meters, even though they are installed indoors and not at optimal at all. But in terms of a good installation, like a good antenna, not the small antennas that you get when you buy your 5Ps, but a large fiberglass antenna, and you install it on the top of your roof or a high building, you can go really far. And I know that you might have an example.
Yeah. In fact, the next one is a bit of a kind of last 5 minutes is for an esoteric application, and these have to do with very long LoRa links. So we said that LoRa, you can go long distance, but now we're talking. Look at that. This is something that Frederick, in fact, sent me, picking up from Kalmar some packets which are 300 kilometers far away. So really far, and there's no way you can go on a terrestrial links, because you have the earth is not flat, of course, so you have the curvature of the earth, which at 300 kilometers would require both sides to be on very high mountains. We're talking about 4,000-meter mountains on both sides, which is not the case. And so in the past, there has been many examples of this. So there's many anecdotes on the TTN channels, on Twitter, and so on. People say, unbelievable. I mean, I get these super long links, hundreds of kilometers, and what's wrong? And then, some people reply, it's, the software that doesn't work. It's not true that you get all these long links. And some other people have some very, strange explanations. But, being, in a physics center, we know that it has to do with physics. And in fact, this was on Twitter. It was quite kind of interesting. This was on Sigfox network, and they said that they had a tracker, a small GPS device, which was in Spain, and it was picked up by a gateway which was in Italy, so 1,300 kilometers far away. And they had no explanation how that was possible. And the explanation is that you have what is called tropospheric propagation. So that is a phenomena that actually, people have been witnessing for long, right? I'm sure that in Sweden, sometimes you pick up FM signals from, other countries far away. And that usually happens in the summer. And you get these, FM radios, maybe especially in the old days when, that was all analog and wasn't digital, or even TV for, far away. And that happens because you have this tropospheric propagation. So the troposphere is a layer which is about 10 kilometers above, the Earth level, and you have like different temperatures. So you have a temperature on the ground, on the Earth, and then at a higher level you have a different temperature. and you get this inversion layer where the radio signals kind of bounce. And you have different conditions. So you have, the normal condition where you just get at a certain level, but then you have this ducting condition where the signal kind of bounces on the tropospheric layer, and you can get super long links, incredibly long links. So what we did as a research, we kind of studied how that, can happen in case of LoRa signals. And that, again, you have a cooler, moist air, and then on top you have a warmer, dry air. And that, again, usually happens over the sea in the summer. And so, again, this signal bounces off and it reaches, very long distance. So what we did is installing some IoT nodes, very simple IoT nodes, the LOPI that you have in the lab. In our place, this is here in northern Italy. It's the blue dot. And then we checked who is receiving this signal. And through TTN, you can find out the gateways that are receiving your signal. And in our case, it was this place called Cesena, which is 200 kilometers away from Trieste. But in other places that we had another node in Sardinia, it was picked up by a gateway in Barcelona that is 584 kilometers. And point is that we didn't do that once. We did it in a scientific way to show that it was tropospheric propagation. And in fact, there's 18,000 packets received in Cesena. So this is not like a one shot that happens by chance. And then if you look at on the longer term, you see that it happens in the summer and you get many, many packets through. So this was kind of interesting because for the first time, we kind of documented in an experimental way that LoRa also offers this tropospheric propagation. And in fact, there's, some calculations that you can carry out. This is physics of the troposphere, where you have this refractivity gradient. And we actually showed, scientifically that those were conditions of this, super refractivity and of, tropospheric propagation. So that might happen in Sweden as well. In fact, as Fredrik, sent me, that happened in Sweden, where you have this 300-kilometer link, which can only be explained by the tropospheric propagation. So this is an example just to show that you can carry out research, even with, very low cost devices, open, TTN infrastructure, and it's a super low cost experiment. We can be published because it's, scientifically sound. And I think that was my last slide. So my point is that we carried out that with TTN, with 20,000 gateways. I would really like to do the same experiment with helium, because now you have 80,000, 800,000, right?
Yeah.
So maybe that single packet can be picked up by many more gateways.
I should put a node on my car when I'm driving down and to Italy this summer. So
yes, definitely, yeah.
Maybe that will not be too much tropospheric, but yeah, absolutely, that would be super interesting. So, and let's see what happens in the course. Like it would be really nice to see how many people that are actually using, because this year we've never actually had this many gateways, LoRaWAN gateways installed. So the third year we have this course. The first year it was like very few students that used LoRa. Second year, well, many more. And this year I really hope that many will explore it and try out how it works. So
yeah. So when I'm sure that when Pietro will explain about MQTT, then you will get the whole picture, right? Because from the application server, then you need to get your data out in some way, and MQTT is the way to go.
Yeah, we spoke a little bit about MQTT earlier today as well when we were visited about TOIT. But next week will be more about
MQTT,
like the cloud side of the IoT. So
sure.
Yeah. So I thank you very much. There are no more questions at this moment, but I know that you're hanging around in the server as well. So you might be able to join in and answer if there is anything that comes up later on.
Absolutely. If there's any question, just drop me a line either through email or on Discord, and I will be happy to answer.
So thank you very much, Marco.
Thank you. Thank you for the invitation.